Welcome, Algebra 1 students, to Unit 1.1, Classifying Real Numbers. You are hearing the voice of Mr. May, and I will be your teacher for this unit. Before we begin, please make sure that you have your guided notes available because you will be completing them as we work through this unit together. One other thing I would like to encourage you to do is use your pause and rewind buttons. Use your pause button to make sure that you fill in the blanks correctly. And also please make sure that you use that rewind button to go back and review any content that you may be somewhat uncertain about. The benefit of having a video is that you can go through and review at your own pace and work through all the examples and the content at your own pace. So please make sure that you use the pause and rewind button to make sure that you fully understand the content. Again, this is Unit 1.1, Classifying Real Numbers. And in this unit, our learning targets, we will have 3 of them, which you will notice are correlated to the unit number. So you'll see learning target 1.1a, 1.1b, and 1.1c. You will be able to follow these learning targets all the way through both this unit and the examples, as well as the exit slip and practice problems that you will be working on. If you understand these learning targets, then you will be prepared for any content and questions that may be associated with them. So our first learning target, 1.1a, is I can classify numbers appropriately in the real number system. Now notice this is classify. So given a set of numbers, you will be able to, again, classify them appropriately in specific categories, which we'll learn to call these category sets. Learning target 1.1b is I can represent data with plots on the number line. You may be familiar with a number line showing the different numbers, again, that we will be classifying. So we're going to take these numbers that we're classifying and we're going to be placing them on a number line with plots representing data, but also in their appropriate location. And then finally, we will be working up to this learning target a little bit. It may carry over to a couple of different units or sections in this unit, and that is learning target 1.1c. I can explain why the addition of 2 rational numbers is rational. Again, that word explain, that verb is very important. That goes beyond the ability to just recognize or identify. It implies a greater understanding of what is going on when you add 2 rational numbers. And so we will be building on that verb, explain. So a lot of this content that you're going to learn in this particular Unit 1.1, as with all math, will carry over as we increase our ability to really achieve that learning target verb of explain. So let's begin with definitions. Our first definition is going to be one of the classifications of real numbers, and that is going to be our natural numbers. Now, natural numbers are going to be the ones that we are very familiar with, and one of the first numbers or sets of numbers that we learn. Whenever you play hide and seek, and you say, I'm going to count to 10. You say 1, 2, 3, 4, 5, and so on until you get to 10. So we also call natural numbers, sometimes you hear them called counting numbers. These are all positive numbers. So that's very important to remember. Only positive numbers. And so we will begin at 1. And naturally, when you think about it, again, natural numbers, when you think about someone that tells you, I'm going to go hide when we play hide and seek, rarely does someone begin with 0, 1, 2, 3, 4, 5, and so on when they're counting. Usually, and most commonly, the counter begins with 1, and that is where natural numbers begin. They do not begin with 0, they begin with 1. So 1, 2, 3, and so on forever or until infinity. If we were to write 3 more natural numbers. I'm going to encourage you to hit pause here, write 3 more natural numbers, and then I'm going to write 3 more. So the 3 that I'm going to choose, I've already mentioned them. We talked about counting for hide and seek. 4, 5, 6. Each of those, again, is a positive number. It is a counting number, but again, it does not have to be contained from 1 to 10. I could have just as easily written 1010, 1011, 1012, and of course, they don't have to necessarily be in order. So a third example could be if I were to just choose 2,224, 3,176, and 4,001. Each of those is considered a natural number. Again, it does go on forever. Our next classification, which we'll also call a definition, is a whole number. If you look closely, try to determine the difference between the natural number and the whole numbers. What is different when you look at the examples that are given? Possibly you have already recognized that difference, and that is the inclusion of 0 within the set. So when we talk about whole numbers, it includes all natural numbers. So we also have all natural numbers are in this set. All natural numbers plus, or in addition, or also including, and then we have included 0. So that is the only difference between the natural and whole numbers. So again, hit pause. See if you can write 3 more whole numbers. 3 more whole numbers. Well, that one could be tricky because you think, all right, we've got 0. That's the only additional number that's in this set. But remember, we also said that we include all natural numbers. So we could just as easily use the same numbers from the previous classification of natural numbers. So we could have just as easily said 4, 5, and 6. Those are both natural and whole numbers. They carry through. Remember, they have to be positive numbers. We could just as easily say 111, 227, and 342. Any positive natural number is also included within whole numbers. The only difference is, once again, the inclusion of 0 in the set. Our third classification, integers. Take a moment, see if you can recognize what additional numbers are included inside of this set. You may have recognized or noticed now that we have negative numbers included. So now we have the inclusion of negative numbers within the set. Also notice, just like with whole numbers, we carry over previous sets. As we enlarge our sets, as we enlarge our classification, we're carrying over our smaller or previous classifications and sets. So we also have 0, which we know is a whole number. So 0, for example, is both a whole number and an integer. The numbers 1 and 2, as you may recall, they are a natural number, a whole number, and also integers. So integers will include both natural numbers, whole numbers, and now the inclusion of negative numbers. So go ahead, write 3 more integers, hit pause. And if I were to add 3 more integers, I'm going to add a variety here. I will include a -4 because negative numbers are integers. I will also include a +3 and a 71. Each of those is considered an integer, both positive and negative numbers along with 0. So now we have 3 sets. We have natural numbers, whole numbers, and integers. Our fourth definition or classification of a real number includes rational numbers. Rational numbers are a little less straightforward than our natural, whole, and integers. However, they do have a very distinct qualification that allows them to be classified as a rational number. And as you may notice, I did not include necessarily specific numbers because I want to highlight that a rational number is any number that you can write in the form of this is an A divided by B, so written as a fraction, where A and B are integers. So notice that we are working with integers in our fraction. So both A is an integer as well as B. Remember, integers include both positive and negative numbers and the number 0. One other thing to point out, B cannot equal 0. This is something we will discuss further, but B cannot equal 0 because we cannot divide by B without getting an error. So when we take a fraction with 2 integers, and one in the numerator, one in the denominator, and we write that in decimal form. So if we were to write that in decimal form, what we would end up with, and this is where the definition of a rational number really concludes, we have either a terminating decimal or we have a repeating decimal. So let's take a moment and look at what a terminating decimal looks like. Well, a terminating decimal is going to be something that ends. Terminating and in are pretty much the same term. So let's, for example, look at a terminating decimal. So we have our decimal point, 1.25. Notice that 1.25 has an ending. It ends at 5. It does not go on forever. It does not have any additional numbers after it. And so we call this a terminating decimal. That does not limit us to just 2 decimal places. It can be any number of decimal places. I could have just as easily written 1.76. That is also a terminating decimal. Another example, what if I were to say 4.0? Well, 4.0 is also a terminating decimal. But what is it also the same as? You may be familiar with the ability to drop the 0 because it does not add any additional value to that 4, and we could have just as easily written it as 4. Now what this brings up is an additional property that we've already kind of discussed, and that is numbers from smaller classifications carry over into the larger classification. So 4 was a natural number. It's also a whole number. It is also an integer, and now we know that it is a rational number. So all the previous sets of numbers that we've classified and defined carry over into this set of rational numbers. So we can call every one of them rational numbers. Now, we've discussed terminating decimals. We also have to talk about repeating decimals. So a repeating decimal is exactly what it sounds like. And you may be familiar, one of the most common is you may see 0.33333 goes on forever. Sometimes we abbreviate it as 0.33 with a little bar above it called 0.33 repeating. And so 0.33 repeating is a rational number because that 3, the 3's repeat forever. Now, if I were to write this in a fractional form, that would be 1/3. 1/3, 1, just to go back to our definition, 1 is an integer. 3 is an integer, so I have two integers. 1 divided by 3 is 0.3 repeating, meaning that we can classify 1/3 or the decimal form 0.3 repeating as rational numbers. And so this is also the case with any other set of repeating decimals. So if we were to write 3 more rational numbers, go ahead and hit pause, write 3 on your own. And I will write 3. I'll begin with writing one that would be considered a terminating decimal. So a terminating decimal, we'll just say 5.735. That is a terminating decimal, and let's highlight that as a terminating decimal. That way, okay, so that is a terminating decimal. And let's do one more terminating decimal with, we could just say 2.5. 2.5 is another terminating decimal. So let's go ahead and highlight that green as well. And then our repeating decimals, let's see, our repeating decimal, well, we know that 1/3 is a repeating decimal, but also 2/3 is a repeating decimal. And if we were to enter that in the calculator to get the decimal form, we would see that it is 0.6 repeating. So now we have 4 sets of classifications. We have natural numbers, we have whole numbers, integers, and rational numbers. However, unlike what we have seen so far, where one set builds into another, we're going to create or classify another set of numbers that does not include any of the numbers we mentioned before. So we are actually going to identify numbers that do not fall in any of these 4 classifications, and those we will call irrational numbers. So irrational numbers are defined, once again, we have A and B are still integers. And one thing I do want to point out, that B cannot be equal to 0, once again, because we're dividing by that B. And what is going to happen with these? They cannot be expressed in that form because they will neither terminate, so these do not terminate, and do not repeat when written, and I'm going to make a little note here, when written in decimal form. So if we were to take 2 integers and we were to divide the integer A by the integer B, we would not get a decimal that is nice and friendly and terminates or repeats. What it looks like is nonsense, pretty much, because you have a series of numbers that just 7, 8, 4, 3, 1, 0, 2, 7, 6, 1, 3, 8, 9, and on and on and on forever. And if you look at this decimal, the side of the decimals right here, notice that there is no perceivable repetition. Can't make a pattern necessarily to see that it repeats over and over forever. It does not terminate because even though I stopped at this last 9, even though I stopped here, these dots imply that this number would go forever and ever and ever. It never stops. And for this reason, we call these types of numbers irrational. And so a couple of things that you may notice with irrational numbers is when you enter them in a calculator, you will see just a very, very, very long decimal that does not terminate and does not repeat. Now, the types of numbers that you'll see and mostly work with that fall into this category are going to be square roots, for example, and it would be square roots that aren't perfect squares. And we'll talk a little bit more about perfect squares in future units, but a square root that is not a perfect square. So for example, the square root of 5, if you were to enter that into your calculator, you would see that the square root of 5 does not terminate and it does not repeat. And so that would be considered as an irrational number for that reason. And so another that you might see, and just to let you know before I move ahead, the square root of 5, if you were to enter it in your calculator, is 2.236067797749979, and that is where my calculator actually stops attempting to show me or display any more numbers. And so again, that would be an irrational number. One of the more famous irrational numbers is pi. And most of you may know that it begins with 3.14, but it once again continues forever without repetition. And so these are two irrational numbers. Take a moment and see if you can determine 3 more irrational numbers. So 3 more irrational numbers would be a great place to start with irrational numbers would be with square roots. And so those that aren't perfect squares. So another imperfect square would be the square root of 7. We could also look at the square root of 12. And another square root that we could consider is square root of 21. Once again, there are infinite numbers of these irrational numbers, but they are a separate set. You will not see an integer, for example, like 3, the number 3, and I'm going to write it in a different number here. Let's write it in green. If I were to write the number 3, this would not be considered an irrational number because if I were to look at the properties of this number 3, we will see, first of all, that if I were to add a decimal, I would add a 0 to make it 3.0. Well, that 0 doesn't add any value, but it does create a terminating decimal. And a terminating decimal, as you know, is a rational number, and rational numbers also include integers, whole numbers, and natural numbers. So in this case, this would not be considered an irrational number. Irrational numbers are a completely separate set of numbers. So our last couple of definitions. A set. I've used this word many times throughout this unit so far, and what a set is a collection. It is a collection of well-defined, distinct objects that share common It's important, common properties. Now, most of us are probably familiar with collecting. Maybe you collected baseball cards. Maybe you collected figurines. Maybe you collected something else. Video games. It doesn't matter. Music. You could collect any amount of things. But when you have a collection, usually you put them in a set. And I know with baseball cards, you may have a set where you get an entire team, or you may get all the teams for a particular season. And it's called a set. You have all of them. And what defines them are their common properties. Well, we're doing the exact same thing, except in our collection is a collection of numbers. We are collecting numbers. And the numbers that we're collecting, we are then placing in a set. And each of these sets, we are then giving a name. And those names that we are giving our set are natural, whole, integer, rational, and then I'm going to specifically write irrational in a different color because it is not included in the set of these other numbers. So we have to maintain that distinction when we talk about our set. So again, a set is a collection. In our case, we're collecting numbers. We're placing them into sets with common properties, and we talked about the common properties in each of the definitions, and then we give those sets a name so that we can identify them for future purposes. Now, our last set, and this is our largest set that we've talked about so far. Our last set are real numbers. And the reason we call them real numbers is because there are actually imaginary numbers that you will work with in the future. Not necessarily in Algebra 1, but in higher math level classes. But there are imaginary numbers, so that's why we have to make the distinction of real numbers. Now, within this real number set, we have two very large sets of numbers. We have our rational numbers, which you may notice we have already defined and classified. And we also have our irrational numbers, which we have defined and classified. And so together, these two sets of numbers compose our set of all real numbers. So all the numbers that you're used to working with or having been familiar with up to this point, we consider and call real numbers. Definition, lastly. This is actually a property that is very important to all of our real numbers. Now, to begin with, the generalization of it, the closure property states that an operation, now an operation, let's talk about that word for just a moment, an operation meaning addition, subtraction, multiplication. So that is what we're referring to when we talk about operation. Performed on any two numbers from a set. Now this is singular because we have a set. So we have a set. So from the set of, we could say real numbers. We could also say from an integers. Our integers is a set. Our natural numbers is a set. Irrational numbers is a set. It's any of those classifications or definitions that in this previous slide, I'm going to go back one slide. Any of these that we called a set, once again, we can highlight these, are all sets of numbers. So going back, from any one of those sets results in a number that is contained in that same set. What this means is that if we take an integer and we were to perform an operation, and that operation we'll say is addition, and we were to add another integer to that, we would get a number that is in the set of, in this case, integers, because we have a set. Again, it does not have to be integers. This is the example that I'm using. And when we perform an operation, in this case, our operation was addition, the result, and anytime we see the word result, we often tend to think of equals a number that is also in that contained in the set. Well, the set that we're working with in this case is integers. And then a little additional definition, but really just kind of an addendum to the closure property is that the closure property holds for all real numbers. For all real numbers. Now that is very important, and I'm going to really underline this all. This means that all real numbers are closed. Again, they closed. It means it holds to the property of the closure property. Okay, it holds to the closure property under the operations, and once again, we're using operations of addition and multiplication. Notice that subtraction and division are not included. That is very important. Subtraction and division are not included. The closure property holds for addition and multiplication, meaning that if we take an integer and add another integer, we will get an integer. If we take a natural number and we add another natural number, we will get another natural number. If we take a rational and add a rational, correct, we'll get another rational number. It holds under the property, the closure property, for all real numbers. So example number 1, this is highlighting Learning Target 1.1a. Take a moment, hit pause after you read through the question, and the question is, where would you place each classification in the Venn diagram? And the Venn diagram being this entire set of rectangles. And so to give a quick explanation, you would consider the smallest rectangle as one set that you would place a classification that we've previously defined. You would consider this next size rectangle as the next set. You would consider the next rectangle as the next set. And then you would also consider the largest rectangle as the next set. Finally, you have this rectangle is the last set that you would classify. So take a moment, think about where you would classify each of the sets we have previously defined. You will have a set in the yellow box, the pink, the green, the blue, and also the final box on the side over here. So hit pause and see what you think would be the proper classifications. Okay, welcome back. If you look and think about at the diagram, notice first of all, this rectangle is the smallest set. It's the smallest rectangle representing the smallest set. So if you think about which set we defined that was the smallest, our smallest set that we defined was our first set. It was the set of natural numbers. These again, where the numbers are counting numbers, 1, 2, 3, going on forever. Now, if you recognize at this point that maybe you have gone the other direction with your sets, you can hit pause, you can erase, and you could come back, you could correct, and you could check against what I am going to finish with going forward. So, thinking about one of the properties that I discussed when we were going through our original definitions and classifications was that smaller sets are also included in the larger sets. So what is the next largest set that we discussed? Well, that's going to be inside of this set of rectangle, this rectangle here. And that was our whole numbers. And remember, the only difference between a whole number or the set of whole numbers and the natural numbers is the inclusion of the number 0. So you get 0, 1, 2, 3, and so on and so forth forever. Only positive numbers. At this point, you may realize that our next set, which it would be contained in this rectangle, I will highlight it green once again. We're going to now include negative numbers. Well, the set that includes our negative numbers would be the integers. So you might end up with -2, -1. Our whole numbers, in this case 0, is included within our integers, as well as our natural numbers or our counting numbers. And the integers go forever in both directions, the negative direction and the positive direction. And lastly, on this side of our classification, I'll highlight it as blue. If you recall, our natural numbers, whole numbers, and integers are all considered rational numbers with the inclusion of terminating and repeating decimals. So all of our natural whole integers, as well as terminating and repeating decimals. And just to avoid confusion, I will also write repeating decimals. So now we've accounted for our natural whole, integer, and rational numbers, but that still leaves one set to be defined. And if you recall, that one set to be defined could not be included with any of these other sets of numbers. We have to distinguish it and set it apart from our other sets because it does not include anything that could be a terminating or repeating decimal, an integer, a whole number, or a natural number. These are our irrational numbers. And again, we gave the probably most famous example of pi, and then any of our non-perfect square roots. I think we use the square root of 5, the square root of 7, and other square roots that end in non-terminating, non-repeating. So just to do not terminate and do not repeat. So there are the 5 sets of numbers that we defined, and you may recall our largest set that contains both rational and irrational numbers, and that is the set of real numbers. Remember, real numbers are the set of rational and irrational numbers. So example number 2, we talk about number lines. And so with a number line, you may be familiar with putting numbers on a number line. And when we look at the number line that's given in this example, and this example once again is going to highlight learning target 1.1b. So example number 2, learning target 1.1b is what we're highlighting. And we have a number line that is given to us at the bottom. And just to discuss briefly a number line as maybe a refresher, if we were to, in general, divide it in half and put a 0 in the middle, numbers moving in this direction would be our negative numbers. Numbers moving to the right would be our positive numbers. And this is our set of all real numbers. And so if I were to put numbers in general, our integers, because we got both positive and negative, if we were to add the integers to this, we would say 1, 2, 3, 4, 5. And in this direction, we would have negative 1, negative 2, negative 3, negative 4, and negative 5. So we have our integers. So that leaves the question of where would our rational and irrational numbers fall? Well, look, once again, they are decimals, and the distinction between them is whether or not they are terminating or repeating. And if they're terminating and repeating, they will be rational numbers. And if they do not terminate and do not repeat, they will be irrational numbers. And so if we were to place those types of numbers on the number line, they would fall between our integers, somewhere in between. And whether they repeat or terminate will determine if they are classified as rational or irrational. So those are the numbers that are going to fall between our integers on this number line. And so when we look at the numbers given, let's read our example. Our example says Coach DeBoard collected data on the number of home runs hit by players on the BCHS softball team. His results showed the following numbers of home runs hit by each player during the season. Plot the data on the number line. Well, a couple things we have to notice. First, when we look at the numbers, what types of numbers in general, if we were to classify them, what do we have? Well, pretty much looks like our natural numbers. We don't have zeros, so we're not going to consider it a whole number. We don't have negative numbers, so we wouldn't necessarily say integers, but natural numbers do fall in every single one of those sets. But if we were to look at the most basic set that we could call this, we would call this our natural numbers. And we have to place these somewhere on the given number line. Now, what I tend to do is I tend to look at the smallest number because I've got to label this number line. So I look at the smallest and the largest number given in the data set. Well, my smallest number is a 1 and my largest number is a 9. So on my number line that is given, I need to be able to have a smallest value of 1. And again, when we look at the numbers on a number line, moving to the left, the numbers get smaller, and moving to the right, the numbers get larger. So my smallest number, it would make sense to put over here on the left. So number 1. And then the easiest method is to just fill in the numbers from there, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And notice that 9 is also included on my number line. So I have accounted for the entire range of data that's given. And so to plot these values, what I will do is I will take a dot for each number and I will place it above the corresponding space on the number line. So let's begin with this number 7. Well, notice that I marked it out because I don't want to forget a number. That is one of the most common mistakes that I see, is that we overlook or forget to include a number from a large data set. It's not as hard on this data set because there's only 1, 2, 3, 4, 5, 6, 7, 8 numbers. But as we get larger and larger sets of data, it's easy to forget one of the numbers in the data set. So as I place the dot above the corresponding spot on the number line, I'm going to mark it out in my data set to make sure I don't forget any. So there's 7. 4, place a dot above the 4. 6, so I'm going to place a dot above the 6. And notice here that we have a 7 repeated. We have this 7 that is repeated again. So what this says is that 2 people on the team, 2 players on the Boyle County High School softball team, had 7 home runs. And so we don't ignore that fact. I want to be able to look at this number line and easily tell that there were 2 different players that hit 7 home runs. So what I'm going to do is I'm going to put a second dot above the 7. Now, I would encourage you to make sure that you make sure there is space between the 2 dots. And don't put the 2 dots, for example, right on top of each other where we can't tell what the data is telling us. We want to make sure that we can easily and quickly look at this number line and tell how many players correspond to each one of the numbers on the number line. So there's my 7 that I've placed on there. So let's 6 and 7. Now there's the 9. So dot above the 9. 2. Our 1. And once again, we have another repeated number. So in this case, we'll put a second dot above the 2. And I'm going to go back and double check to make sure that I have accounted for all my numbers. So if I go back and count, I have 1, 2, 3, 4, 5, 6, 7, 8 numbers in the data set. I should have 8 dots on the number line. Please, whenever you are plotting data on a number line, go back and double check to make sure you have all the dots. So I have 1, 2, 3, 4, 5, 6, 7, 8 dots. So I've accounted for all my data. I can easily see how the data is laid out on the number line, and I have accounted for and included the entire range of values on my number line. It's also neatly organized, and I can easily and quickly evaluate and analyze the data. Example number 3. This highlights learning target 1.1c. And so working through this example, the first question is, what is the sum of the following numbers? Well, sum, if you recall from previous math classes, sum refers to the operation of addition. And so we're going to be adding the following numbers. But more importantly, what we want to learn is what classification these numbers are going to be. So let's take a look at the first number that we will be adding, and that is 1.25. Well, it has a decimal, so it can immediately narrow the classification into one of 2 sets. It's either going to be a rational number or it's going to be an irrational number, because those are the only sets that include decimals. The question then is, does 1.25 repeat or terminate? And in this case, it terminates. So that leads us to conclude that 1.25 is a rational number. Our second number, 3.83. Take a moment, see if you can determine what you think the classification of 3.83 should be. Excuse me. Okay, using the same logic as before, we know it's a decimal. We know that it does terminate. So that will lead us to the conclusion that we have a rational number that we are working with. So we have two rational numbers being added together. And so adding these together, we end up with 5.08. And so the classification of 5.08, correct, is a rational number using the same logic that we had before. It is a decimal, meaning that it could be either rational or irrational. 0.08 terminates. Therefore, we have a rational number. Looking at our last question, and this really highlights 1.1c, learning target 1.1c. What property of real numbers explains this result? So thinking back at all the properties that we have discussed, one in particular, that property was the closure property. And I would encourage you to hit your rewind button, go back, listen to the explanation of the closure property once again. But in summary, what that closure property says is that any operation, and in this case our operation was addition, performed on any two of the same set of numbers, okay? Numbers from the same set. In this case, our set that was being added in the same set that was being added was a set of rational numbers. And then the result, the closure property states the result, and we said another way that we represent result is with the equal sign, equals, the result equals a number contained in the same set. Well, the number that's contained in that same set is 5.08, and it is a rational number. So we use the closure property to show that two rational numbers added together resulted in a number classified as rational. And lastly, the addendum to the closure property was that it holds for all real numbers for addition and multiplication. And we have already verified that we're using addition because of the word sum. And so in this case, a rational number added to another rational number results in a number that is also contained in the set of rational numbers. So lastly, if we were to think about it, what type of number would you get if you summed any two rational numbers? Any two rational numbers. What type of number, what classification would this fall under? This would fall under the closure property, which tells us that any two numbers that are rational, that are added together, will result in a rational number. So this concludes Unit 1.1, Classifying Real Numbers. Please, if there is any content that you do not feel comfortable with, go back and review it. That is the benefit of having a recording. Work through the examples again. Make sure that you're familiar with them. And as always, if you have further questions, please seek out additional help from any of the math teachers. They are more than happy to help you further understand and fully understand any of this content. Thank you for your attention. Thank you for your time. Thank you for your efforts. Have a great day and see you in class.